In a circular tunnel 27 kilometers in circumference, buried on average 100 meters below ground level on the French-Swiss border, is the world's biggest experiment. The Large Hadron Collider, the LHC, is the most powerful particle accelerator ever built, capable of ramming together two beams of protons so violently that each proton has an energy of up to 7 trillion electron volts, about the same as a flying insect. The total kinetic energy of a proton beam in the LHC, when at full power, is roughly equivalent to the energy of a Nimitz-class aircraft carrier moving at 10 kilometers an hour. Why the need to concentrate so much energy into tiny particles? One of the most fundamental questions in science is why there are different types of particles and forces. In a true theory of everything, the subatomic zoo would reduce at high enough energies to a single animal. This holy grail of physicists, which would also see the unification of quantum mechanics and the general theory of relativity, probably lies a long way off, but a first step towards it might be a grander scheme of nature beyond the standard model, known as supersymmetry. One of the predictions of supersymmetry is that for every ordinary particle of matter there ought to be a superpartner, a squark for the quark, a selectron for the electron, and so on. A goal of the Large Hadron Collider, then, having already discovered the Higgs boson, is to look for signs of these superpartners amid the shrapnel from high-energy collisions. To have a chance of spotting any of these suspected superpartners, physicists have to arrange for conditions that haven't existed in the universe since a split second after the Big Bang, and in a form that can be closely studied. At earlier and earlier times, the universe was an increasingly simpler place in terms of the variety of stuff it contained. Particle physicists deal a lot with the concept of symmetry. When the cosmos was brand new, it was highly symmetric in the sense that there was no difference in strength between the four fundamental forces. Then, in an inconceivably tiny moment after time itself began, gravity broke away from the other three forces, like a crystal condensing out of a solution as the solution cooled. Later, as the cosmic temperature fell further, the strong force declared independence, and finally the symmetry between the weak force and electromagnetism was broken. If supersymmetry is a fact of nature, then it too must have been broken at some point well within the first microsecond of cosmic time. Before that point, the known fundamental particles today, the various fermions and bosons, would have existed alongside their superpartners in equal numbers. But after the breaking of supersymmetry, the superpartners would have disappeared. The only way to conjure them back into reality, if they ever existed, is to recreate for human observation the ferociously hot esoteric soup of particles known as a quark-gluon plasma, which filled the universe in that long ago era. Hence the need for the LHC, a genesis machine designed to restage, in a sense, the first few moments of the cosmos. Think microscope, fridge and vacuum chamber rolled into one. Then think the biggest and most extreme of all these things, and a picture of the LHC begins to emerge. It may seem odd that it takes the largest instrument ever made to find out more about the smallest objects in nature, but high energies are the key to unlocking the secrets of nature at its finest level, and repeatedly nudging charged particles to higher and higher speeds with powerful magnets is the only way to reach those energies. The faster a particle travels, the harder it is to bend its path into a circular shape. To reach speeds of 99.999999% of light speed, even using some of the strongest magnets ever built, demands an enormous turning circle, which explains the LHC's extravagant size. The magnets themselves are as big as the trunks of large oak trees and hollow, so that the particles being accelerated can pass right through the middle of them. Underlying the strength of the LHC's magnets is a bizarre effect known as superconductivity, which can only be understood in terms of quantum mechanics. When some substances are cooled way down, they become able to pass an electric current, a flow of electrons, without any resistance at all. This means it's possible to make a hugely powerful electromagnet using coils of superconducting wire, because a very large current can be passed through the wire without any losses through heat, which in turn gives rise to an intense magnetic field. The niobium-titanium wires at the heart of the LHC magnets are chilled to within a couple of degrees of absolute zero, the lowest temperature that's theoretically possible. To maintain this level of superfrigidity throughout the approximately 7,000 magnets spaced around the LHC's vast donut-shaped track calls for about 100 tons of liquid helium. Failure of a superconducting magnet when part of its coil system jumps back to a normal state of resistance is known as a quench. This can happen when the magnetic field strength gets too high, which destroys the superconductive state, or variations in the field strength are too large, which cause local hotspots, which in turn cause the breakdown of superconductivity. Just over a week into startup operations of the LHC in 2008, a section of about 100 magnets unexpectedly quenched, leading to an immediate shutdown of the whole collider. About 6 tons of liquid helium vented into the main collider tunnel. The local fire brigade was called out as a precaution, an inquiry followed, and there was a delay of more than a year before the LHC returned to the business for which it was intended, smashing together subatomic particles at record high energies. Faster and faster the particles, protons, race around the collider in 2 oppositely spinning beams until they're travelling so fast that they can complete over 11,000 circuits of the 27-kilometre long ring each second. Nothing must get in their way until the time is right for the 2 beams to collide, and for this reason the internal pressure is kept at 1/10 of an atmosphere, 10 times less than the near-perfect emptiness on the Moon, and as good a vacuum as nature has to offer anywhere in the solar system. When the protein beams are eventually allowed to crash into each other at any of 4 principal experimental stations located around the main ring, the result is up to 600 million collisions per second and spot temperatures 100,000 times higher than those in the Sun's core. Needless to say, the LHC is a power-hungry beast, consuming enough electricity to run 120,000 California-style homes. The 4 main detectors plus 2 smaller ones where collisions take place and the outcome registered are housed in vast underground chambers as big as cathedrals. 2 of these detectors, called Atlas and CMS, are general-purpose instruments that spearheaded the hunt for the Higgs and continue to do so for supersymmetry particles. The other 2, known as ALICE and LHCb, are used to carry out detailed studies of the quark-gluon plasma and also to seek clues to what happened to all the antimatter that was supposedly created along with ordinary matter when the universe was new. The 4 major experiments, when in full cry, spawn a staggering 15 million gigabytes of data every year, or roughly 1,000 times as much information as is contained in all the new books printed annually. To crunch all that data calls for computing power on an epic scale and is provided by thousands of computers and storage systems scattered across hundreds of data centers in 34 countries, making up what's called the worldwide Lhc Computing Grid. The great thing about the Large Hadron Collider is that whatever it discovers, it will revolutionize science. Finding the Higgs was stupendous because it completed the Standard Model and solved one of the great outstanding problems in physics: why elementary particles have mass. Now we can look forward to finding out more about physics beyond the Standard Model. Positive and negative outcomes alike will be fascinating and deeply revealing. But the fact that the LHC is opening up new realms of science and probing unprecedented regimes of high energy also means it has the potential to spring surprises. Some of the entities it gives rise to in its Big Bang mimicking smash-ups may be exotic and unpredictable in their properties. Early in its career, the LHC survived several lawsuits aimed at shutting it down, and Earth, along with the rest of the space-time continuum, has survived the LHC. But as physicists prepare to restart this mightiest of particle colliders for its third major run, doommongers continue to ask whether the experts can be trusted, or if the LHC really is on the brink of triggering Armageddon. We'll look at the science behind these concerns in the next video.